This video is for people who used to use MATLAB for signal processing and now making their way to Python to gain most basic experience in data analysis, because I believe this is a familiar concept and a good way to start off for those and myself as well. As you can see, I got all necessary packages exported to begin with. I will mention later what each of them are used for when there's need. First thing I do is to create a class named signal, since I'm going to use more than one functions defining these signals. So when writing this method, I aim to initialize and rearrange the variables of a function. To recall that variables later, I need the self parameter. Then I line up the essential parameters for a signal. That's it. At this part, you can either go blank or assign a value to them to make them actually initialized, but I don't need in this case, at least for like amplitude and frequency, because I will manually change them. The key point here is the phase angle, because there won't be any changes for the phase, and it has to be a fixed value for all the signals I'm going to create. I skipped the part where I redefined the variables as themselves again. Now we're back with time step. What is time step? It is the time between each point in the signal. Think of it like increment range in a time axis. Then there's time axis, of course. I'm using numpy arrange, and that generates a time array starting from 0 up to the specified duration, but with the step size of time step. I think I made it clear. In the next method, I'm just defining the sinusoidal wave formula. It has nothing to do with algorithm. It's just an approved formula in physics, but pay attention how I adjusted the green def writings to be aligned. Otherwise, it causes an error. For this video, I'm going to be creating 3 separate sinusoidal waveforms, so there's no need to create an additional method for cosine. After I'm done with methods, I'm starting to define each signal under class signal. From now on, you can change the values however you like, but all I can say is that the more you increase the amplitude, the bigger values you get on the y-axis, and likewise, the more you increase the sampling rate, the bigger values you get on the x-axis. And soon I'm going to show what happens when you change the frequency. Finally, I take the sum of all 3 in the name of signal, which refers to y-axis on the first plot we're going to get. Well, for the x-axis, obviously, it's got to be time axis, but notice that it is signal 1 time axis. Why is that? Actually, it doesn't matter whether you write signal 1, signal 2, or signal 3, because their time axes are all the same as their sampling rate and duration are the same. After modifying the plot, we say plot show, and we get the plot. Let's see what happens in the waveform when you give greater values for frequencies. I expected them to get much more closer, as if they're squeezed by the sides. Exactly like this. And what I mentioned earlier, if you changed time axis from signal 1 to signal 2, there are not going to be any changes. As you can see from the plot, I go back to my original values for easier observation, but before we move on, let me explain briefly what is fast Fourier transformation. It basically transforms time domain signals into frequency domain. This helps analyzing the components of a signal, allowing us to observe some important data such as amplitude, phase, and frequency. For the rest of the video, I'm going to pretend like I'm not given any of the properties above, and I will try to get each of their components from their summation graph. For this step, the only thing I did was to use FFT from SciPy, but it doesn't say too much about the components by itself. On the x-axis, there is our sampling rate multiplied by 2, because this is even function, and on the y-axis, there are amplitudes proportional to Fourier coefficients. The magnitude of the Fourier coefficients will increase as the number of sample increases. If we don't normalize, we don't see the actual values, so it is an essential step to normalize the graph. The most simplified explanation would be divide FFT with n over 2, where n is your sampling rate. As I proceed to get new plots, it provides us a better understanding, because now you see the amplitudes are getting closer to the values I chose to be. However, on the x-axis, sampling rate remains, which I want to get rid of, and see frequency range instead. So for the next sequence, I'm using FFT frag function to convert the sample indices into their corresponding frequency values. By the way, I wrote sampling rate again just to indicate it. If you already have it written above, you don't need to write it twice. And as we've already got the correct spectrum of amplitude, there's no change in this as well. Now this time on the x-axis, I've got what I wanted because now there's frequency and amplitude. It's not the final view, but even from this, you can clearly see the corresponding frequencies to the amplitudes, or vice versa. Since the FFT of a real value signal is asymmetric and I only want one-sided plot, I'm going to use RFFT because RFFT computes the FFT only for positive frequencies. As you can see, it has the same structure with the FFT function, so it's not something new. Please pay attention that I'm multiplying the amplitude by 2. The reason is that we discarded the negative frequencies, so we double the amplitude to account for the missing half. Finally, we get the plot that indicates the given values in the beginning, yet we can improve it a little bit more by marking the exact frequency values on the x-axis. And this is pretty much it. Thanks for watching.